me in doing this.
Thank you. For about your question, I think it's quite clear
Okay, very good.
what you intended.
Now, let's go back to our hydrogen atom problem. Remember, after we realized that we were making statements we were not allowed to make by putting a delta function, the first thing we did was to exclude high momentum components. And how did we do that? We took our potential, we Fourier transform it, then we regularized it, which means we introduced a cutoff. For instance, a smooth cutoff, but it doesn't have to be a smooth cutoff, of course. It can be a step function. And then we anti-Fourier transform it. So this was V lambda, because now the potential depends on the cutoff. And then when you anti-Fourier transform it, you get a V lambda of R, a regularized potential. Okay, now we are sure that this potential doesn't mess up. And by mess up, I mean doesn't couple soft degrees of freedom to hard degrees of freedom that are outside of my Hilbert space. So it doesn't bring in actors I don't want to be brought in. Is that clear? Now, in our specific case, the potential consisted of two parts, a Coulombic potential and an unknown hardcore potential. So if you want to regularize this potential, we have to, the Fourier transform is linear, luckily. So I can regularize both interactions here. And we began by thinking that we have to regularize the Coulomb potential. So let's say Coulomb potential goes into the Fourier transform of the Coulomb potential, which is negative E squared over Q squared. Now this goes into regularized Fourier transform of the Coulomb potential. And then you can anti-Fourier transform. And if you look at the notes, I think this will generate an error function as a regularized version of the Fourier transform. So basically, you will get Coulomb times error function for the regularized version of the Coulomb potential in coordinate space. But now the question is for you. No, actually, I will put it as a question for you. I will discuss it all together. Suppose we are not interested in this very particular problem. Suppose we are really interested for a moment in the real Coulomb hydrogen atom problem. When you studied this, you didn't regularize. You didn't take the pain to regularize, right? You never mentioned regularization where you studied the hydrogen atom in the first place, did you? So was that garbage? How come you get fantastic results and you claim victory because you compare to the spectrum and even the hyperfine spectrum and everything was fitting so well, never having to mention regularization? Now I'm telling you, everything needs a regularization. How come things worked before you even knew about regularization? Okay? It's a bit like when you start learning of quantum mechanics and you begin wondering, so how come that I've been using Newtonian physics for 2 years, never running into problems? Was that all wrong? How come it worked so nicely and now you're telling me energies are quantized? Yeah, we're in a similar situation. So we need to explain why things worked, even without having to think about regularization. Okay? And I think there's a very nice explanation for that. And I think I will convince you very much. So let's look at the potential energy V of Q in Fourier space. it's basic. Oh, let me take the modulus. I don't want to go negative. That's 1 over q squared. This is q, right? So the spectral representation of this potential is like this. And it's a fast decreasing polynomial. Now, the typical momenta where you get a final result here are the typical momenta of atomic physics. How do I understand what are the typical momenta of atomic physics? Well, for instance, I take a Bohr radius, 1 angstrom, right? Roughly speaking. It's not exactly 1 angstrom, but we know that more or less that's it. Then from 1 angstrom, I say, okay, the typical momentum is going to be h bar over 1 angstrom. Roughly speaking, okay? That's a typical momentum exchanged by, say, the electron and the proton. Okay? Fine. Now, regularizing means graphically that I substitute this with a new potential that at some point goes exponentially down. Because here is no longer this, you get an additional exponential fall off. Do you agree? Now, this exponential fall off, this is scale lambda. This function is basically 1 for q squared much smaller than lambda, but becomes exponentially decreasing when q squared becomes over the lambda square, right? Then you start seeing that your function contains an exponential, right? Because if you Taylor expand this is 1 minus q squared over 2 lambda square, and this is much smaller than 1 when this is much smaller than 1. Now, clearly, if this scale is much larger than h bar over 1 angstrom, so it's a momentum that are typical, say it's 100 times larger, then really you're making 0 something that is already 0, and you're making exponentially small mistakes. Now, since in atomic physics there is a gap, I have nuclear physics starting off here at very large energy. I have atomic here. And I can choose because there is a gap, a lambda that is sufficiently large to be much larger than any atomic physics, yet still smaller than nuclear physics. Then putting the cutoff doesn't make any difference whatsoever. Well, the worst that can happen, you can change this by, say, 1 per mil, and I can reincorporate that by just readjusting the electric charge by a little bit and say maybe, but even so, there's no need to do that, because this is going to be a correction on the tail of a tail of a tail of a wave function that I will never be able to measure unless I have energies at which I start worrying to be able to excite nuclear physics. Is that clear?
Yes.
Okay, so that's why things worked, because we had a gap. Physics modeling starts, rigorous physics modeling starts when you have a gap, because you can choose lambda and you can do this game. Now let's come back to us. We know, however, that in our case, there is unknown physics much before the nuclear physics scale, because our potential is the Coulomb potential plus a hard core. And we know that this hard core sets in much before nuclear physics. How do we know? Because we look at the famous data of delta E over E, and we discovered that there were disagreements of order 1 already for the ground state. So there was some energy already at the atomic scale. This is playing a role. But maybe it doesn't play a role in the very soft atomic physics, only in the hard atomic physics, yet at the atomic physics. Okay, so we have to regularize this And we expect this regularization to become important because it's not far away in the sky, is only a couple of, maybe a factor 2, 3 shorter. Okay? Okay, so let's do the regularization game. We take u of r, we go to the Fourier transform of u of r, which becomes u of q. We regularize u of q. Okay, now comes the point. I don't know u of q. How can I know its Fourier transform, not to mention its regularized Fourier transform? Now comes the point. I know that I'm interested only in momenta that are much smaller than the cutoff. So this means that, if you write the Schrodinger equation, let me write the Schrodinger equation. You're all familiar with the Schrodinger equation in momentum, in position representation, right? That's the stationary Schrodinger equation. Now, of course, you can Fourier transform this guy and you get the Schrodinger equation in momentum representation, right? I don't know if you have ever seen it, but I think you're not surprised to find out that the kinetic energy operator becomes diagonal in momentum representation, of course, but the potential is no longer diagonal, and what you get is actually a convolution between the wave function. And of course, then you have this term here. Now, this expression tells me that the potential couples modes. These are maybe I write it a little bit better because my script is very horrible. So let me just redo this. Schrodinger equation in momentum representation. The Fourier transform of a product is a convolution. So that's why you get q minus p psi tilde of p, for instance. And then, of course, you have the other part here that is basically the same as in the other Schrodinger equation. So let me write it this way, equal E psi tilde of P. Now, you see, my wave function, my system is soft, which means that this wave function will only have soft components, correct? The spectral representation of wave function will only have Fourier components at momenta much smaller than the cutoff, which means that this integral with the no, even if this function can have hard components, the potential, all I need is this function coupling soft modes, because it is involved in a convolution with a function that only contains soft modes. So the large exchange momenta will be suppressed. The large P momenta contribution here will be suppressed by this product, okay? So in other words, if I'm interested in only soft physics, all I need to have is the soft components of this Fourier transform. So Q, I'm not interested in all this. I'm interested in this at momenta much smaller than the lambda. So what do? I Taylor expand it. I have a zero coefficient. I have a second order coefficient. I'm going to tell you why I don't have a linear coefficient. And then I put a cutoff. So first of all, this is the Taylor expansion of U tilde of Q. And this is the regularization. These are unknown coefficients. Because I don't know U, I cannot know the Taylor coefficients. So the Taylor coefficient, this is the first term. I put no linear term. And the reason I put no linear term is that I assume my potential is spherically symmetric. If to have a linear term, I would have something like a vector of coefficient Q dot, say, U1, right? Because you need to build a scalar and Q is a vector, you need a vector, right? Which means that U is not spherically symmetric. So if my interaction is not spherically symmetric, I need also some extra Taylor expansion. So by selecting certain terms in the expansion, I'm using symmetry. So this is knowledge from outside, if you want. So I'm being completely general here. All the information, I know nothing. I want you to appreciate this. I'm not waving my hand and building a model based on physical intuition now. I'm doing things systematically. I'm saying I'm regularizing here. I can choose any regulator because this is simply to exclude large momentum physics. And in building the Fourier components, I'm retaining only soft distance physics because I'm building an effective theory for soft dynamics. That's my choice. But within that choice, I'm being completely rigorous because I'm making no assumptions here, except from letting symmetry guide me. The only guidance I need to know about the ultraviolet physics I want to study is its symmetry properties. So it is not quite true that I'm asking to know nothing about the ultraviolet physics. I'm asking nothing except general symmetric properties. For example, suppose we want to study a quantum field theory or a relativistic quantum field theory, and there is some short distance physics I don't know. I still require that the principle of relativity holds in the ultraviolet sector, even if I have not tested it. I can also avoid doing that. But if I avoid doing that, I must include also all the terms that violate that symmetry, right? But you see, symmetry. So do you get this point? Is anybody confused about this? Please.
Just for clarity, it's that we extend the symmetry we know in the IR regime to the UV, or we need a way to know the UV symmetries.
Haha, that's a very, I was about to get this. I'm not sure I grasped completely your question because you're very faint, but let me try to interpret it. What I said so far is that we are assuming, in order to write the most general form for this ultraviolet physics we don't know, we are assuming we know its symmetry properties. Okay? Is it something we can possibly hope to be doing, or is it not? After all, I told you, we do not have access to ultraviolet physics. How can we hope to know something about the ultraviolet physics? And now I seemingly contradict myself and say, no, well, let's assume we know the symmetry of the ultraviolet physics. It looks like a contradiction, right? But I'm now going to tell you that symmetry is the only ingredient in a theoretical modeling that is scale independent. Why? Because symmetry implies one fundamental observable thing. Who tells me what is the main implication in terms of observation of a symmetry? Normally.
The constants of some quantities.
Invariances, exactly. Invariances or conservations? Okay, for those of you who have a high energy background, they know the Nether theorems and blah, blah, blah. Fine, you know this. For those who don't, let me tell you one thing. Suppose you have your Hamiltonian. Now, suppose you have, what is a symmetry? A symmetry is a transformation of my system that doesn't change my system. Take a perfect ball, perfect spherical ball, paintless, completely homogeneous in paint and rotate it. You apply a transformation to your system, but you're unable to detect the changes induced by your transformation, right? That's a symmetry. Now, at the quantum level, a symmetry is a transformation of your wave function. Let U to be your transformation of the wave function. Well, you know, if your transformation commutes with the Hamiltonian, then you will discover you can find a set of states that are the eigenstates of the Hamiltonian are the eigenstates of U. And basically what you will discover is that if you are in a given state of U, you will remain in the same state of U forever. In other words, there are conservation laws. Example, the invariance under phase rotation implies charge conservation. The invariance under translation implies momentum conservation. The invariance under rotation implies angular momentum conservation. Now, even though I do not have access to the degrees of freedom above the cutoff, let's suppose one of the fundamental invariances is the number of electrons, the number of baryons remains. Oh, I don't want to use names that are perhaps outside the background of somebody. Say the electric charge is conserved. Suppose at some high energy process violates the electric charge. Well, if this was true, if I would be able to observe processes that even if I don't know what happens inside this process, at some point I count the charge and it's not the same as it used to be before. So conservation laws at low end, I can measure them at low energy because that's what I do typically, but they penetrate the ultraviolet regime, because if I have a break-in at high energy, it will percolate into in the break-in of a quantity that I might be able to detect at low energy. So it is not as entirely true that I know nothing about the ultraviolet scale, because if the electric charge was not conserved by some super high energy interaction, I would have seen more charge popping up than I actually have. Okay? So symmetry norm, or if the Lorentz or translational invariance was violated by energy physics, chances are that I would be able to see it at low energy, right? So basically, all I can say about the ultraviolet is something that doesn't depend on momentum, and conservation doesn't depend on momentum. Okay? It's a pretty tough point to digest. It's not very easy conceptually. Does anybody have doubts about this?
Yes.
Okay, sorry?
Yeah, I have one, because it does happen that some symmetries are broken in high energy regimes. For example, parity violation, time inversion violation, and
Right. When
but it
this
doesn't
happened,
happen in we do not see in experiment in the IR regime.
very good, very good. In fact, that's a great point. I can give you another example. Galilean symmetry. This is not seen in the non-relativistic regime, right? The breaking of Galilean invariance. Well, this means that when you start to seeing these violations, then you have to change your model also at the level of the underlying symmetry and include the terms that are violated by that symmetry, okay? So, in other words, to build an effective model, you need basically lambda plus symmetry. In many cases, in fact, I say chances are, you can detect that symmetries at low energy. Not always, like you correctly point out. But in most cases, from symmetry violation in the high energy regime will reflect in properties that are visible in the infrared. Let me give you an example that is perhaps a bit exotic, but I think you're familiar with in terms of its implication. Spin statistic symmetry, spin statistic connection, right? You know, Fermi spin 1/2 particles must obey anti-commuting commutation relationship, or differently speaking, must obey Pauli principle, right? We know that. But this is a result of the fact that there is relativistic invariance. You do not have that in Galilean invariance. So it's something that occurs at very large energy, because we know that at very large energy I detect that Galilean invariance is no longer a symmetry. That has implication at low energy, because we phenomenologically know that we can never put two fermions with the same quantum states. Okay, but there have been exceptions. There have been cases where at very high energies, only process that occur at very high energy violates the symmetry. And then you are not able to see them unless you go to very high energy. So if this happens, you have to include those terms and write your most general expression for a short distance physics in order to keep track of all the symmetries you think you're valid in the ultraviolet. Okay? Did I answer?
Yes, yes.
Okay, so going back to us, this is taking far too long than I expected, but I like this discussion anyway. I'd rather do one less topic, but get into discussing this very thoroughly. So, okay, so that's why in my writing my phenomenological expression, no, sorry, my rigorous expansion, I did not include my even terms, odd terms here. And of course, here I have my q square over 2 lambda square. Now, what happens when I anti-Fourier this guy? Well, this is basically a smeared delta, right? I call it smeared delta. So the Fourier transform of a delta function, let's look at the first one. The Fourier transform of the first one is the Fourier transform of a constant plus a delta plus a cutoff at very, very large scales. So when I Fourier transform this, the corresponding object in the infrared will be extremely flat at small distances, because the Fourier transform of this will be something like e to the r square lambda over 2 square, right? So whenever r lambda is much less than 1, this will not become important. So basically, one way to see this is that, one way to understand what kind of a expansion, what kind of a hardcore expansion this generates, is to say, okay, let me look at this case, this term only. When I Fourier transform them, I get delta function, Fourier transform of a delta function. I get second derivative of a delta functions. But now remember, there was a cutoff here. So I have to smear all these delta functions as Gaussians. So summarizing everything, the regularization step says my potential will go into new potential, which has a cutoff, which will be likely, now I am there could be some 4 pi floating around. This is the anti-Fourier transform of the regularized Coulomb potential, okay? plus u0 delta function smeared, u2 the gradient of delta function smeared, plus blah blah blah. I've written the most general low energy effective interactions that accounts for unknown physics in the ultraviolet. These terms here are called the counter terms, because these terms have been put in to account for the physics I cannot resolve above the cutoff. And I'm replacing that physics with local terms that are not infinitely local, they are local up to the cutoff scale. Those of you who have done quantum field theory have seen the counter terms. They have put the counter terms. But they're nothing but this. Okay? Okay, good. So now we have a procedure, but we need a third step. You know, we don't know these constants. So the third step is to fit the constant. And what is the name of step 3? You know, it amounts to a fitting procedure of the constant, but it has a very, very high sounding name, renormalization. Which basically means that I have a number of, say, suppose I'm interested in retaining only the first term, U naught. I have now two constants.
I think I've missed the second step.
First step, choose the cutoff. Second test, exclude the Hilbert space from the cutoff. Probably 1 and 2 were together.
Okay.
I don't know if I distinguish them. If I resolve them into 2 steps or in 1, but we understand. Next step is renormalization. Right? Now, like I said, it is likely, in principle, you know, remember what I said before. Let's forget for a moment this. This was the Coulomb potential, and then we were setting it to 0 at some scale lambda. In principle, for lambda short enough, it might happen that I have to slightly adjust this in order to get exactly the result I was getting before without cutting off the high momentum scale. But since normally this never happens, I don't have to worry about that. But in principle, now I have at least 2 or more unknowns to determine in order to be predictive. They play the same role as the multiple expansion. These are the effective parameters or effective couplings of the theory. And they have to be determined, and I have only 2 ways to determine. If I know what is above the cutoff, and I'm only interested in an effective theory for practical reasons. For example, I know nuclear physics and I am interested in atomic physics, I can use nuclear physics to compute these quantities, say. Or if I don't know that nuclear physics, I can measure it to compute it. I can fit these coefficients. So I can either microscopically compute can you hear me? Hello?
Yes.
Yes.
Because there was a message on the screen that the Zoom was about to crash and it didn't. Okay. Or I can measure it, which means fit. So in particular, let's forget about this because we said, let's leave aside this because we had this discussion that, we can choose the cutoff so that it doesn't really matter. Let's focus on this term here. So basically, what do? You choose your lambda, say, to be a third or a fourth of an angstrom, assuming the cutoff has a range much smaller than that. That's your choice. Then you define Gaussians. In every function you write, you will have smeared functions with that particular value. Okay, so sorry. Let's suppose I regularize with a scale A, which is h bar over p. That's my momentum cutoff lambda. And instead of defining a momentum cutoff, let me now define a length cutoff. And let's suppose this is some fraction of the angstrom, say 0.3. I'm just choosing something which is reasonable because I know that something's going on here. Okay, I'm going to vary this later and see what happens. Okay, if there is a gap, the precise value of the cutoff shouldn't matter. Remember, if there is no gap, it should matter dramatically. But we are assuming that there is a gap. So this is Coulomb, 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 and then at some point it blows up or it goes down in a non-Coulombic way. Okay, the hardcore. So let's assume A is somewhere here. Then, of course, my regularization will be r squared over 2a squared. So everything that was a delta becomes a Gaussian. So for instance, delta lambda becomes delta A is going to be some kind of now I'm not worried about exact normalization. You can pick it up in the books for three-dimensional Gaussian. I think this is to the 3/2 or something. Doesn't matter. That's what I write. This is what I mean by delta A. And then, of course, I can take second derivative of these guys because it's a perfectly smooth function. Okay. And so I have all my terms. So for each of these terms now, given the choice of A, I can use the first. Suppose I'm adding only the delta term, not the second term. I will have to, given a choice of A, I will compute the energy spectrum for for different values of the corresponding constants U naught. And I will choose the U naught that provides the best agreement with the lowest energy state. In other words, I will fit the prediction to the ground state. So if you do that, let's go back. Delta E over E. This is 1, 10 to the minus 1, 10 to the minus 2, 10 to the minus 3. So this is the 1s, 2s, 3s, 6s. So suppose we now sacrifice 6s to find U naught. So we are in the same situation we did with the phenomenological delta function. Remember, sacrifice 1 point. But now, instead of using the delta function, I'm using a mere delta function. Okay? Because the delta function was the phenomenological approach, and now I'm doing the rigorous effective theory renormalization group-based approach. So let's go back and see how the results look like. Rather than me drawing them, let me go and tell you how they look like. And I should probably save them into Acrobat so I don't have to do this all the time. Good. Look at this. This is really amazing. Now, the curve here, I don't know if you can see the cursor. I don't think you can see, but the topmost core is ignoring the hard core altogether. And you get an error that is always greater than, say, 10%, okay? And it becomes of order 1 as you move forward. The next curve was the phenomenological model we did before. And even if it contains the same numbers of parameters, the very same numbers of parameters, right? The accuracy is 2 orders of magnitude larger. And in the worst possible case, it will be below 10% error in 1S case. But you did, the number of parameters in your fit was exactly the same. You only were careful enough to exclude the high momentum scale. But then you add only one more term, and you get an error for the lowest energy state that is 10 to the minus 6. And it remains less than 10 to the minus 2, except for the ground state. So this curve shows you how powerful the renormalization group procedure is actually turned out to be. Do you see this? It was simply the right thing to be doing. Things weren't working well because we were not doing the right thing. We were messing up high energy, low energy, making statements we had no control. Once you do things with control in a proper way, then clearly you see you get not only more theoretical control of what you do, but you get far better results. I want to emphasize, though, that as you go towards high energy, no matter how many parameters you include, you're going to get worse. Okay? Because you're moving close to the cutoff when you begin to start resolving the ultraviolet physics. And it's exactly the same thing as trying to solve the multiple expansion problem and getting close to the charge. No matter how many multiple terms you fit, when you get closer and closer, you get worse and worse. So in other words, if you're very far, you can get the same accuracy with fewer terms. But when you get close to the cutoff, in order to get the same accuracy, you need more terms. Eventually, when you get at the cutoff scale, when new physics sets in, your effective theory will break down because you will be inaccurate no matter what. And the reason is simple. You have a Hamiltonian that doesn't know all the degrees of freedom in your system. Imagine this. You know, you are doing nuclear physics, but you only know about protons and you don't know about neutrons. Of course, you got nuclear physics wrong. They are at the same energy scale. They all participate to the dynamics. Okay? That's so I have been teaching this for 10 years more or less. And anytime I go through this, it's like a revelation to me. How can this not be the right way to do? And how strange we do not learn it from the day one in school. Of course, it's difficult to teach a freshman about this. But I think it's quite weird that we arrived to the last year in theoretical physics education without ever hearing about this. and thinking about renormalization group as a mathematical trick. It is not a mathematical trick. It's a physical statement about what can we say and what we cannot say. I want to mention one important point. What happens if I slightly change the cutoff scale? Question mark. Remember, in the renormalization procedure, say, okay, fix the cutoff, and in our example, we fixed A, then compute to fit the parameters, and then compare to data. Now, clearly, if I switch this, my potential will change, right? So at least in principle, also my constants will change, because in order to fit it to the data, since my potential has changed, I have to twinkle them a little bit to get the right result. Now, now comes the discussion we had at the beginning of the lecture. If we are really in the atomic physics situation where I can put the cutoff very far from any physics that is before and after, then clearly changing the cutoff doesn't do any appreciable consequence, right? Because all before I start resolving new physics, I must go so far away. But really, life is not always as gentle as atomic physics. Very often we are in situations like this. So most of the time, by changing the cutoff, I'm gonna exclude some physics. And even if the physics, say, nuclear physics is still here, but I like in the case we are studying, nuclear physics is still very far away, but there is some hardcore physics I don't know. And maybe, remember, this is the Coulomb, maybe my cutoff was here or maybe here. It will produce slightly different results. So I have to refit. So basically, this means that my effective parameters in general are expected to have a weak dependence on the cutoff. And if I'm doing things properly, this dependence should be weak. By weak, I mean logarithmically, hopefully, but certainly not very powerful dependency, okay? This fact, which is nothing by what happens if you fit a function, in theoretical physics goes under a very high sounding name. We say that the coupling constants run with a cutoff. Running coupling constants. Okay? How many of you have heard of running coupling constants in different contexts, typically high energy physics?
I did.
Okay. For example, right. I mean, the typical example is the strength of the fundamentals, strong interaction, right? The coupling constant, well, the coupling constant of QED, E squared over 4 pi, is expected to run, but is expected to run only at very large energy, where you you already have ground electroweak unification. So QED is never in the game. But the coupling constant of the strong interaction runs at the scale of 150 MeV typically, which means that if you probe in nuclear physics with very high energy, you will have a weak coupling between particles that are strongly interacting, quarks and gluon. But if you probe it with low energy, you will see a strong coupling. So in other words, when quarks get very, very close to each other, they interact very weakly. And when they're far away, they're very heavy. This is the Nobel Prize for Physics, I guess, in 1998. I mean, the discovery was done in the 70s, but the Nobel Prize was granted in the 90s, late 90s. So the concept of running coupling constants looks very mathematical when you see it in quantum field theory for those who have done it. I don't care about quantum field theory here. From the point of view of understanding the physics behind it, is just fitting the effective parameters of the theory. Okay, so there's nothing so mystic about renormalization group theory. It's the way of thinking that we will adopt in the rest of this course. Never, always think about what physics can you separate, what is hard and what is soft, and always try to do physics for the soft. And now finally back to our questions. Can I really go all the way to the roof? Of course not. Every theory I've done, including the standard model, is a theory that assumes there is a gap between the regime of Hilbert space where you test the models and the parameters and the regime where new physics sets in. And this gap is essential for you to be able to say, I can be predictive. Now, I like always to close this lecture with what I called the Lagrangian complex. What is the Lagrangian complex? It's my own expression. It's not a general jargon or nomenclature. It's something I used to joke with the students. So you won't find it in literature, okay? It's just my way of thinking about it. So when we grew up in our education, especially in the young age, we tend to be rigorists. We like think when things are elegant, clean, and we don't like when you have too much tweaking. Okay, I guess I interpret many of you, at least I was that way. I was happy anytime I was getting a parameter-free prediction. It felt like I was doing the right thing in the deep of my heart. So let's take the most fundamental theory we have in our science. Who tells me what's the most fundamental theory of physics we have today? Accepted fundamental theory of physics.
General relativity and quantum field theory.
That's the framework, but I'm talking about the theory of interactions and particles. What theory summarizes everything we understand about high energy physics, for instance?
The principle of least action made with Lagrangian dynamics.
Oh no, this is all okay. I agree, guys. You're telling me mathematical things. I'm talking about particles. Is electrodynamics, quantum electrodynamics, a fundamental theory, or is an effective theory or something else, according to today? So we do, with a cutoff at a tera electron volt, so to say, that's as much as people have been able to resolve. what is the most fundamental, most microscopic description, most beautiful achievement of humanity in terms of fundamental theory? I mean, that,
The G-2 experiment.
okay, no, I'm not able to. I was trying to get this, the name standard model out of you. So the standard model, sorry, it's probably my fault. I was trying to, the standard model is a theory for quarks, gluons, weak leptons, matter fields, including, quarks and baryons and leptons and gauge fields and blah, 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 blah. And it reproduces all of the physics. And that's considered a fantastic theory, is relativistic invariant, renormalizable, which I didn't say what it exactly means, but he has a nice properties, right? It predicts beautifully experiments. And it's considered to be fantastically elegant. Even the Higgs boson was found, right? So let me ask if anybody, so let's now talk about the opposite. Can you claim another physical theory that, of course, holds a lower energy scale that people normally consider as a bit of a dirty fix, too many parameters to tweak, not very clean, not many self-contained, not many theoretically sound theory? Can you guys give me an example? Okay, I'll try to give you. How does nuclear physics, so let's lower the cutoff to the electron volt, right? To the mega electron volt. And people have to deal with nuclear physics, right? And for instance, people deal with nuclear physics potentials. So in the standard model, you have a beautiful Lagrangian with fields and gauges and blah, 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 and everything looks so covariant and beautiful. And then one scale below, you have Hamiltonian, you have, potential V18, 18 parameters, and, some of them have like pion exchange, but a pion isn't really a fundamental particle. Then you have to put there rho, but the rho is not really a particle, blah, 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 blah. So the nuclear physics potential is considered like the paria of the physics compared to the standard model, because it's not relativistic, is it looks very much cooked up. Okay, now if you look at this difference from the point of view of effective theory, there's not really difference between the two, because it's just a matter of where you set the cutoff. If you're working at nuclear physics energy, you probably don't need relativistic corrections, because the cutoff is such that at the energy of the cutoff, the relativistic corrections are small. And then you write the most general potential, that's called the V18, and you're basically doing the same thing as we did before with all the terms we added. You know how many parameters have a nuclear physics potential you have to fit in order to get the data? I'll tell you, 18, because there are just 18 possible ways of coupling nucleons in a tensor way, okay? You know how many parameters there are in the standard model? Anybody knows?
19, I guess.
27. So is the standard model a better theory than the dirty nuclear physics model? Only because we raised the cutoff by 1 order of magnitude, 2 order, 5 order of magnitude. It is certainly more fundamental in the sense that it's more microscopic. But that doesn't imply that it's any better or worse. It's just an effective theory built at a different scale where you have put in different information about the symmetry, particularly the color symmetry, the gauge symmetry, and blah, 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 blah. At the low energies cutoff, much of that symmetry is irrelevant. For instance, the color symmetry is irrelevant because it's confined inside the hadrons. And all you're left with is other parameters to fit. You don't need to use a Lagrangian formulation. Use a Hamiltonian formulation. Why? Because a relativistic covariance is above the cutoff in this effective theory. So we think we are doing superior physics by writing things this way, but we are doing the same things that we are doing here. If you think about this in terms of a rigorous renormalization group-based effective theory, it's just shifting your resolution scale. So this tendency of look at things in a Lagrangian elegant way, thinking that they are better because they look better in the formulas, is what I call the Lagrangian complex. When you go past that and you think in terms of physics and what is real content of your theory, in terms of how many parameters do you need, how large is the gap, and so forth. There are other issues that determine how reliable you are in your theory. And most importantly is how much do you know about the underlying symmetry and how large is the gap. That's what makes a more cooked up theory different from a less cooked up theory, is how much understanding and reliability you have about these two particular quantities. Okay, so I guess in these first 3 lectures, 2.5, I was doing basically no math, but I was trying to set the stage for what will come next. So I suggest we go on as forward. You read Lapage notes, and if you want, you can also watch the lecture I gave online, where I redo the multiple expansion using the language of renormalization group theory. Basically, I renormalize the electrostatics, okay? Classical electrostatics, using these ideas. Then next lecture on Tuesday, we spend some time discussing about this in case you have questions. And then we close this introduction to the course, the prologue. And for a number of lectures, we will dive into mathematics, because we will have to build the tools for the core of the course that will be on complexity, fields, and stochastic behaviors. And we will go into developing tools. In particular, we will develop the path integral formulation. So we'll go deep into mathematics for some times. And then we will start applying mathematical concepts together with renormalization group theory ideas and start describing the physics of complex systems and discover that, you know, how chaos and stochasticity emerges and what are the implications of them. Okay? So if there are no questions, I close the lecture and I will see you Tuesday. Okay?
Okay.
Yes, bye-bye.
Okay.
Bye-bye.
Have a nice
Bye.
weekend.
You too.